Right now, as you sit watching this video, you are surrounded by an invisible war being fought on a scale so vast that it encompasses every atom in your body, every star in the galaxy, and every galaxy in the observable universe. On one side stands gravity, the relentless force that wants to crush everything into a single, infinitely dense point. On the other side stand mysterious forces and quantum effects that push back against this cosmic collapse with precisely the right strength to keep existence itself from imploding. This war has been raging for 13.8 billion years, and gravity is losing. But it's losing by the smallest possible margin, through mechanisms so delicate and so precisely balanced that if any of them shifted by even the tiniest amount, the entire universe would either collapse into a black hole within seconds or tear itself apart faster than the speed of light. Here's what should terrify you. There is absolutely no obvious reason why the universe shouldn't have collapsed immediately after the Big Bang. Gravity is by far the dominant force on cosmic scales. Every piece of matter in the universe attracts every other piece with inexorable gravitational pull. The more matter you have concentrated in one region, the stronger this pull becomes, creating a runaway process that should compress everything into what physicists call a big crunch, the opposite of the Big Bang. Yet here we are, 13.8 billion years later, not only still existing but living in a universe that is actually expanding faster today than it was in the past. Something is actively preventing cosmic collapse with a precision that makes the most sophisticated human engineering look clumsy by comparison. The forces holding our universe together operate with tolerances so exact that if they vary by 1 part in 10,120, a number so large it exceeds the total number of atoms in the observable universe, everything would cease to exist. Scientists have discovered that the universe is held together by a phase. Scientists have together by a phase discovered that the universe is held together by a phase combination of effects so strange and so counterintuitive that they challenge our understanding of reality itself. Dark energy, a mysterious force that makes up 68% of everything that exists, is actively pushing space apart faster than gravity can pull it together. Quantum pressure from virtual particles creates an outward force that operates even in completely empty space. The expansion of space itself generates momentum that carries matter away from gravitational collapse faster than gravity can halt it. That these cosmic stabilizing mechanisms were undiscovered through abstract theory. They were forced on scientists by observations that made no sense according to everything we thought we knew about the universe. In 1998, astronomers studying distant supernova expected to find that gravity was slowing down cosmic expansion. Instead, they discovered the universe is accelerating its expansion. This finding was so shocking, so contrary to expectation, that it took years of confirmation before the scientific community accepted that some unknown force is literally pulling the universe apart faster than gravity can pull it together. The implications of this discovery extend far beyond astronomy. The mechanisms preventing cosmic collapse are the same forces that determine whether planets can form around stars, whether stars themselves can achieve stable nuclear fusion, whether atoms can maintain their structure, and whether consciousness can emerge in a universe that remains stable long enough for complexity to develop. Leading cosmologists like Alan Guth, Carroll, and Brian Greene have spent decades unraveling the physics of cosmic stability. What they've found suggests that our universe exists in an extraordinarily special state, balanced on a knife's edge between collapse and dissolution, maintained by quantum effects and dark energy fields that operate according to principles we are only beginning to understand. This isn't just academic physics. The mechanisms that prevent universal collapse are intimately connected to the fundamental nature of space, time, energy, and matter. Understanding why the universe doesn't collapse reveals deep truths about the structure of reality, the role of quantum mechanics on cosmic scales, the nature of empty space itself, and perhaps most remarkably why the universe appears to be fine-tuned for the existence of complexity and consciousness. The story of cosmic stability is really the story of how the universe creates and maintains the conditions necessary for its own existence. It is about forces and fields that operate beyond our direct experience, but determine everything from the formation of galaxies to the possibility of life itself. It's about how quantum mechanics, general relativity, and thermodynamics work together to create a cosmos that can support the emergence of stars, planets, chemistry, biology, and ultimately beings capable of contemplating their own cosmic context. By the end of this exploration, you'll understand the precise mechanisms that keep the universe from collapsing, why these mechanisms are so remarkable, how they operate across scales from quantum to cosmic, and what they reveal about the fundamental structure of reality. You'll see how dark energy, quantum fluctuations, cosmic expansion, and gravitational dynamics combine to create a universe that's not just stable, but actively evolving toward greater complexity. But this journey begins with a simple question that leads to extraordinary answers. If gravity always attracts and never repels, if every piece of matter pulls on every other piece with inexorable force, why doesn't everything just fall together into one massive black hole? The answer to this question reveals some of the most profound discoveries in the history of science. If you're fascinated by the deepest mysteries of cosmic existence and want to understand the forces that literally hold reality together, subscribe and hit the thumbs up button. And here's a mind-bending question. If dark energy is constantly creating new space between galaxies, where does this new space actually come from? Drop your thoughts in the comments. I'll pin the most brilliant answer. The universe's battle against its own collapse is the most fundamental struggle in existence. It's a battle being fought in every cubic centimeter of space, every moment of time, through mechanisms so subtle that we've only recently begun to detect them. It is the story of how reality maintains its own existence against the most powerful force in the cosmos. Now, let's begin our investigation into the invisible architecture that prevents the universe from collapsing into nothingness. Starting with the discovery that changed everything we thought we knew about the fate of the cosmos. Chapter 1. Gravitational paradox. Every piece of matter in the universe is trying to destroy the universe. This isn't hyperbole or dramatic exaggeration. It is the stark reality of how gravity operates on cosmic scales. Each atom in your body, each grain of sand on Earth, each star in our galaxy, and each galaxy in the observable universe exerts gravitational attraction on everything else with relentless, inexorable force. According to our best understanding of physics, this should have caused the entire cosmos to collapse into a single point within moments of the Big Bang. The gravitational paradox begins with understanding just how powerful gravity becomes when applied to cosmic scales. While gravity is by far the weakest of the four fundamental forces, weaker than electromagnetism by a factor of 1036, it has one crucial advantage over all the others. It always attracts, never repels, and it affects everything that has mass or energy. This means that as structures grow larger, gravity becomes progressively more dominant until, on cosmic scales, it overwhelms all other forces completely. Consider what this means for cosmic evolution. In the early universe, immediately after the Big Bang, all the matter and energy that would eventually form galaxies, stars, and planets was compressed into a region smaller than a proton. The gravitational attraction between all this matter was absolutely enormous, strong enough to create pressures and temperatures that exceeded anything we can reproduce in our most powerful particle accelerators. Under these conditions, gravitational collapse should have been instantaneous and irreversible. Albert Einstein was the first to fully comprehend this paradox when he developed his field equations of general relativity in 1915. His equations revealed that matter and energy curve spacetime in ways that naturally lead to gravitational attraction. But when Einstein tried to apply his equations to the universe as a whole, he encountered a shocking problem. The equations predicted that any universe containing matter would either collapse under its own gravity or expand forever, accelerating as it grew. There was no stable, static solution. This discovery troubled Einstein so deeply that he modified his own equations by adding what he called the cosmological constant, a repulsive force that could exactly balance gravity and allow for a static, eternal universe. Einstein later called this modification his greatest mistake, but modern physics has vindicated his cosmological constant as one of the most important concepts in cosmology. What Einstein dismissed as an error turned out to be the key to understanding why the universe doesn't collapse. The gravitational paradox became even more acute when astronomers began discovering the true scale of cosmic structure. In the 1920s, Edwin Hubble's observations revealed that we live in an expanding universe filled with billions of galaxies, each containing hundreds of billions of stars. The total amount of matter involved in this cosmic structure was staggering, roughly 80 kilograms of ordinary matter spread across billions of light-years of space. The gravitational forces involved should have been more than sufficient to hold expansion and reverse it into catastrophic collapse. But Hubble's observations showed something else remarkable. The universe wasn't just expanding. It was expanding in a very specific way that seemed almost perfectly designed to avoid gravitational collapse. Distant galaxies were receding at velocities precisely proportional to their distance, exactly what you would expect if the universe had emerged from a hot, dense initial state and was expanding according to the gravitational dynamics predicted by general relativity. This relationship between distance and recession velocity, known as Hubble's law, revealed that the universe was walking a cosmological tightrope. If the expansion had been slightly slower, gravity would have halted it and reversed it into collapse. If the expansion had been slightly faster, matter would have dispersed so rapidly that gravity could never have assembled it into stars and galaxies. The observed expansion rate seemed to be balanced with extraordinary precision between these two catastrophic extremes. Theoretical calculations by Alexander Friedman and Georges Lemaître in the 1920s showed that this balance was accidental. It emerged naturally from the gravitational dynamics of an expanding universe filled with matter and radiation. Their solutions to Einstein's field equations revealed that the universe's expansion rate depends critically on its total density. If the density exceeds a critical value, gravity overcomes expansion and the universe collapses. If the density falls below this critical value, expansion accelerates and prevents structure formation. The critical density turns out to be remarkably small, about 6 protons per cubic meter of space on average. This seems like almost nothing. The best laboratory vacuum chambers contain trillions of times more matter per cubic meter. Yet this tiny amount of matter spread throughout cosmic space generates gravitational effects strong enough to determine the ultimate fate of everything that exists. But here's where the paradox becomes truly mysterious. Observations of ordinary matter, stars, gas, planets, black holes, all the stuff that astronomers can directly detect, account for only about 5% of this critical density. If ordinary matter were all that existed, the universe would have expanded so rapidly that gravity could never have assembled matter into the complex structures we observe. Stars would never have formed, planets would never have coalesced, and galaxies would be nothing more than thin, dispersed clouds of isolated atoms. This realization led to one of the most profound discoveries in modern physics. Most of the universe consists of invisible, exotic forms of matter and energy that interact primarily through gravity. Dark matter, which makes up about 27% of the total cosmic density, provides the additional gravitational scaffolding necessary for structure formation. Dark energy, which comprises about 68% of everything that exists, creates a repulsive force that prevents total gravitational collapse while allowing local structures to form and persist. The discovery of dark matter and dark energy transformed our understanding of the gravitational paradox. Rather than being a problem that threatens cosmic stability, gravity becomes part of an intricate balance, involving multiple components that work together to create a universe capable of supporting complex structure. Ordinary matter provides the material for stars and planets. Dark matter provides the gravitational framework for large-scale structure formation, and dark energy provides the expansive force that prevents everything from collapsing together. But this balance is far more delicate than anyone had imagined. Steven Weinberg's calculations in the 1980s showed that if dark energy were even slightly stronger than observed, it would have prevented star formation entirely. If it were slightly weaker, the universe would have recollapsed before stars had time to produce the heavy elements necessary for planet formation and life. The observed strength of dark energy appears to be fine-tuned to an accuracy of about 1 part in Y-day, a precision that exceeds anything achievable through human technology. This extraordinary fine-tuning of cosmic parameters has led to intense debate about the nature of our universe and our place within it. Some physicists argue that we observe these precisely balanced conditions because we exist. Any universe without this balance wouldn't produce observers capable of making the observation. This anthropic principle suggests that the gravitational paradox might be resolved not through physical mechanisms, but through selection effects. We live in one of the rare cosmic environments where gravity and expansion are perfectly balanced because unbalanced universes do not produce beings like us. Other physicists have proposed that our universe might be one of countless universes in a vast multiverse where different regions have different physical parameters. In this scenario, most universes would indeed collapse or disperse catastrophically, but rare regions like ours would achieve the delicate balance necessary for complexity and consciousness. The gravitational paradox would be resolved through cosmic statistics rather than fundamental physics. But perhaps the most remarkable aspect of the gravitational paradox is that it is still actively being resolved in the universe around us. The battle between gravity and expansion isn't a relic from the early universe. It is an ongoing process that determines the formation of every star, every galaxy, and every larger cosmic structure. Gravity tries to compress matter into increasingly dense configurations, while expansion and dark energy work to disperse it. The outcome of this cosmic struggle determines whether our universe continues to support the complexity necessary for life and consciousness. Recent observations from surveys like the Dark Energy Survey and the Planck satellite have provided increasingly precise measurements of how this gravitational paradox plays out in practice. They've revealed that the universe's expansion is actually accelerating. Dark energy is becoming more dominant over time, suggesting that the long-term fate of the cosmos is continued expansion rather than eventual collapse. But they've also shown that local gravitational systems, like galaxy clusters, can still overcome cosmic expansion and continue to grow through gravitational assembly. This ongoing resolution of the gravitational paradox reveals something profound about the nature of our cosmic environment. We live during a special epoch when the universe is old enough to have formed complex structures, but young enough that dark energy hasn't yet completely overwhelmed gravity. This epoch might be temporary in the far future. Accelerating expansion might prevent the formation of new structures and eventually tear apart even the structures that exist today. Understanding the gravitational paradox, therefore, becomes crucial for understanding not just how the universe avoids collapse, but how it maintains the conditions necessary for complexity, chemistry, biology, and consciousness. The mechanisms that resolve this paradox operate across every scale, from quantum fluctuations to cosmic horizons, creating a universe that is both stable enough to support lasting structures and dynamic enough to continue evolving toward greater complexity. But the gravitational paradox is only the beginning of the story. The mechanisms that prevent cosmic collapse involve forces and fields that operate according to principles so strange and counterintuitive that they challenge our basic understanding of space, time, and matter itself. The next piece of this cosmic puzzle involves understanding how empty space itself generates pressure that pushes against gravitational compression. Chapter 2: Galactic Dissolution. While individual stellar deaths mark the beginning of cosmic darkening, the ultimate fate of entire galaxies reveals an even more profound truth about universal mortality. Galaxies themselves are not permanent structures, but temporary collections of stars and gas destined for dissolution through multiple cosmic processes that operate on increasingly vast timescales. Our own Milky Way galaxy contains roughly 400 billion stars held together by gravity in a magnificent spiral structure spanning 100,000 light-years. This seems like a permanent, stable system. But galactic evolution reveals that even such massive structures face inevitable destruction through gravitational interactions, stellar evolution, and the expansion of space itself. The most immediate threat to galactic stability comes from galaxy collisions and mergers. Despite the vast distances between galaxies, they move through space under mutual gravitational attraction, sometimes leading to spectacular cosmic crashes that completely reshape galactic structure. Our Milky Way is currently on a collision course with the Andromeda Galaxy, and this merger will fundamentally alter both galaxies in approximately 4.5 billion years. Galaxy mergers aren't the gentle collisions you might imagine. When two large galaxies approach each other, their gravitational fields begin interacting billions of years before the galaxies actually touch. These tidal forces distort the spiral arms, trigger bursts of star formation, and fling stars into elongated orbits that stretch far beyond the original galactic boundaries. During the Milky Way-Andromeda collision, most stars will survive the merger itself, since the distances between individual stars are so vast that direct stellar collisions remain extremely unlikely. However, the gravitational chaos will completely disrupt the ordered structure of both galaxies, creating a new elliptical galaxy that astronomers have nicknamed Milkomeda. The beautiful spiral arms that characterize both galaxies will be destroyed forever. But galactic mergers represent only the beginning of galactic mortality. Even after galaxies merge into larger, more stable structures, they face inexorable dissolution through stellar evolution and the gradual depletion of star-forming materials. Each stellar generation converts hydrogen into heavier elements, slowly exhausting the fuel needed for new star formation. The process of galactic chemical evolution follows predictable patterns that lead inevitably towards stellar death. In the early universe, galaxies contained primarily hydrogen and helium, the light elements created during the Big Bang. The first generation of stars formed from this pristine material, living and dying to create heavier elements like carbon, oxygen, and iron. Subsequent stellar generations formed from gas enriched with these heavier elements, allowing more complex stellar structures and longer stellar lifetimes. However, this enrichment process also gradually depleted the hydrogen fuel needed for continued star formation. With each stellar generation, galaxies become less capable of forming new stars to replace those that die. Current observations reveal that galactic star formation rates peaked roughly 10 billion years ago and have been declining ever since. The universe is already past its stellar prime, transitioning from an era of vigorous star formation to a more quiescent phase dominated by stellar evolution and death. Most galaxies today form new stars much more slowly than they did in the past. The Hubble Space Telescope and other instruments have documented this cosmic transition by observing galaxies at various distances and therefore various epochs in cosmic history. Distant galaxies, seen as they appeared billions of years ago, show much higher star formation rates and more chaotic, irregular structures. Nearby galaxies appear more mature and organized, but also less active in forming new stars. This galactic evolution timeline predicts that star formation will continue declining until it eventually ceases entirely. Current estimates suggest that significant star formation will persist for perhaps another trillion years, but at ever-decreasing rates. Eventually, galaxies will exhaust their remaining gas supplies and become unable to form new stars to replace those that die. The expansion of space introduces another mechanism for galactic dissolution that operates on even larger scales. Driven by mysterious dark energy, the universe isn't just expanding, but accelerating. This acceleration will eventually overcome the gravitational forces that hold galaxy clusters together, isolating individual galaxies in an expanding ocean of empty space. Currently, the local group of galaxies, including the Milky Way, Andromeda, and about 80 smaller galaxies, remains gravitationally bound despite cosmic expansion. However, more distant galaxies are already being carried away by accelerating expansion, gradually disappearing beyond our cosmic horizon. In the far future, even nearby galaxy clusters will be torn apart by the relentless growth of space. This cosmic acceleration creates a hierarchy of dissolution timescales. First, the largest structures, superclusters of galaxies, will be stretched apart by expansion. Then, galaxy clusters will dissolve as their member galaxies are carried beyond mutual gravitational influence. Eventually, even binary galaxy systems will be separated by accelerating expansion, leaving individual galaxies as isolated islands in an ever-expanding cosmic ocean. The fate of isolated galaxies depends on their internal dynamics and stellar evolution. Without fresh gas supplies from intergalactic space or neighboring galaxies, star formation will gradually cease as existing reserves become depleted. The galaxy will transition from a star-forming system to a collection of aging stellar populations burning through their remaining fuel. Stellar dynamics within isolated galaxies also contribute to long-term dissolution. Gravitational interactions between stars gradually change their orbits, sometimes flinging stars completely out of the galaxy in a process called evaporation. Over timescales of 1,019 years, roughly half of a galaxy's stars will be ejected into intergalactic space through these gravitational encounters. The remaining stars in evaporating galaxies will gradually spiral inward toward the central supermassive black hole through a process called relaxation. As stars lose energy through gravitational interactions, their orbits decay, eventually leading them to be consumed by the black hole or ejected from the galaxy entirely. After roughly 1,020 years, most galactic stellar populations will have either fallen into the central black hole or been flung into intergalactic space. Black holes themselves play crucial roles in galactic dissolution. Most galaxies contain supermassive black holes millions or billions of times more massive than the Sun. As stellar material falls into these black holes, it releases enormous amounts of energy that can heat and expel the remaining gas from the galaxy, further reducing its capacity for future star formation. The process of black hole feeding also creates jets of high-energy particles that can extend far beyond the galaxy, carrying away material and energy that might otherwise contribute to continued galactic evolution. These active galactic nuclei represent the galaxy's transition from a star-forming system to a black hole-dominated remnant. Even the supermassive black holes that mark galactic cores face eventual dissolution through Hawking radiation. According to quantum mechanics, black holes slowly evaporate by emitting particles, with smaller black holes evaporating faster than larger ones. A supermassive black hole with 1 billion solar masses will take roughly 1,087 years to evaporate completely, but this process is inevitable given sufficient time. The timescales for complete galactic dissolution stretch far beyond current cosmic age. The universe is currently 13.8 billion years old, But galactic evaporation requires periods measured in quintillions of years. These numbers are so large they read difficult to comprehend. The current age of the universe represents less than 1/1,000,000th of the time required for complete galactic dissolution. Yet, despite these vast timescales, the process has already begun. Stellar evolution is already changing galactic properties, removing the most massive and luminous stars. Star formation rates are already declining from their peak values billions of years ago. Cosmic expansion is already isolating galaxy clusters and preparing for the eventual dissolution of larger-scale structure. Observations of galaxy evolution provide direct evidence for these dissolution processes. We can see galaxies at various stages of stellar evolution, from young, star-forming irregulars to old, quiescent ellipticals dominated by aging stellar populations. We can observe galaxy mergers in progress, witnessing the destruction and reformation of galactic structure in real time. Understanding galactic dissolution reveals that even the largest, most stable structures in the universe face inevitable mortality. The beautiful spiral galaxies that populate our cosmic neighborhood represent temporary configurations of matter and energy, destined for eventual dissolution through stellar death, gravitational evaporation, and cosmic expansion. This galactic perspective adds another layer to cosmic mortality, showing that darkness approaches not just through individual stellar deaths, but through the gradual dissolution of the very structures that organize stars into coherent systems. The cosmos is transitioning from an era of galactic construction to an era of galactic destruction, marking another step toward universal darkness. Chapter 3. Accelerating Expansion. The discovery that cosmic expansion is accelerating represents one of the most profound revelations in modern cosmology, fundamentally altering our understanding of the universe's ultimate fate. This acceleration, driven by mysterious dark energy, ensures that the cosmos will not only go dark through stellar death, but will also face a more dramatic dissolution, as the very fabric of space pulls apart all cosmic structure. The story of accelerating expansion begins with observations of distant supernova in the late 1990s. Two independent research teams were studying Type Ia supernova stellar explosions that serve as standard candles because they all reach roughly the same peak brightness. By comparing the apparent brightness of these supernovae with their known intrinsic luminosity, astronomers could determine their distances with unprecedented accuracy. What these teams discovered contradicted all expectations. Instead of finding that cosmic expansion was slowing down due to gravitational attraction between galaxies, they found that expansion was speeding up. Distant supernova appeared dimmer than predicted, indicating they were farther away than expected in a decelerating universe. The cosmos was not only expanding but accelerating its expansion. This acceleration requires a form of energy that works opposite to gravity. Instead of attracting matter together, it pushes space apart. Astronomers call this mysterious component dark energy, and it appears to comprise roughly 70% of the universe's total energy density. Unlike matter and radiation, dark energy maintains constant density even as space expands, providing a steady driving force for continued acceleration. The implications for cosmic structure are profound. For the first 7 to 8 billion years after the Big Bang, matter dominated the universe's energy budget, and cosmic expansion gradually slowed as gravity worked to pull structures together. This allowed galaxies and galaxy clusters to form through gravitational collapse. However, as the universe expanded and matter became more diluted, dark energy's influence began to dominate. Once dark energy took control roughly 6 billion years ago, cosmic expansion began accelerating. This acceleration doesn't just affect the motion of galaxies, it fundamentally changes the nature of space itself. Regions of space that are not gravitationally bound together will be carried apart by accelerating expansion, eventually moving away from each other faster than light can travel between them. This creates cosmic horizons that will shrink over time rather than expand. Currently, we can observe galaxies at distances corresponding to roughly 46 billion light-years due to the expansion that has occurred while their light traveled to reach us. However, accelerating expansion ensures that distant galaxies will eventually be carried beyond our cosmic horizon and will fade from view entirely. The process of cosmic horizon shrinkage follows predictable patterns. Galaxies currently visible at large distances will gradually become more redshifted as their recession velocities increase due to acceleration. Their light will shift from visible wavelengths through infrared and radio, eventually becoming too weak and too redshifted to detect with any conceivable instrument. Eventually, these distant galaxies will cross what cosmologists call the Rindler horizon, the boundary beyond which objects recede faster than light and can never again send signals that reach us. Once a galaxy crosses this horizon, it effectively disappears from our observable universe forever. The information about its existence becomes causally disconnected from our local region of space. Current models predict that within roughly 100 billion years, the only galaxies visible from Earth will be those currently bound within our local group, primarily the Milky Way, Andromeda, and their satellite galaxies. The rest of the observable universe, containing billions of other galaxies, will have been carried beyond our cosmic horizon by accelerating expansion. This cosmic isolation has profound implications for future astronomers. Observers living in the far future will see a universe containing only their local galaxy cluster surrounded by apparently empty space. They will have no direct observational evidence that billions of other galaxies once existed. The cosmic web of large-scale structure that currently characterizes the universe will have been erased from their observable cosmos. The acceleration also affects smaller-scale structures, though on much longer timescales. Galaxy clusters that are not currently gravitationally bound will be torn apart as accelerating expansion overcomes their mutual gravitational attraction. This process has already begun for the largest structures in the universe and will gradually work its way down to smaller scales. Even gravitationally bound systems face eventual dissolution if acceleration continues indefinitely. While objects like our local group of galaxies will remain bound for the immediate cosmic future, continued acceleration could eventually overcome even strong gravitational bonds. In extreme scenarios, acceleration might become so powerful that it tears apart galaxies, stellar systems, and eventually even atomic structures. This ultimate fate is called the Big Rip, a cosmological scenario where accelerating expansion becomes so extreme that it overcomes all fundamental forces. If dark energy density increases over time rather than remaining constant, the Big Rip could occur in as little as 20 billion years. However, current observations suggest that dark energy density remains roughly constant, making the Big Rip unlikely with our current understanding. More probable scenarios based on constant dark energy density predict a different but equally dramatic fate. Accelerating expansion will continue indefinitely, gradually isolating all gravitationally bound structures into cosmic islands surrounded by ever-expanding voids. These islands will evolve independently, following their internal stellar evolution while losing all contact with the broader cosmos. The physics driving cosmic acceleration remains deeply mysterious despite decades of investigation. Dark energy might represent the energy density of empty space itself, what physicists call vacuum energy. Alternatively, it might be a new type of field that fills space and drives expansion, similar to the inflaton field thought to have driven cosmic inflation in the universe's earliest moments. Some theories propose that dark energy is not a new component, but a modification to our understanding of gravity itself. Perhaps Einstein's theory of general relativity breaks down on cosmic scales, requiring new physics that naturally produces accelerating expansion. These modified gravity theories attempt to explain cosmic acceleration without invoking mysterious dark energy. Regardless of the underlying mechanism, observations consistently confirm that cosmic acceleration is real and ongoing. Multiple independent measurements, including supernova observations, cosmic microwave background radiation, and large-scale structure surveys, all point to the same conclusion. Space is expanding at an accelerating rate that will continue for the foreseeable future. The discovery of cosmic acceleration fundamentally changed cosmologists' predictions about the universe's ultimate fate. Before this discovery, the main question was whether expansion would continue forever or eventually reverse into a big crunch. Accelerating expansion makes a big crunch impossible and guarantees that the universe will continue expanding and cooling indefinitely. This guaranteed expansion has profound implications for cosmic evolution. Star formation will eventually cease as gas becomes too diluted to collapse gravitationally. Existing stars will burn out without replacement, gradually darkening the cosmos. Even after stellar death, accelerating expansion will separate stellar remnants from each other, creating an increasingly empty and cold universe. The thermal history of an accelerating universe also differs dramatically from previous models. In a decelerating universe, matter and radiation cool as space expands, but the cooling rate decreases over time as expansion slows. In an accelerating universe, the expansion rate increases, potentially leading to faster cooling and more rapid approach to absolute zero temperature. Current measurements suggest that dark energy density remains roughly constant as space expands, providing steady acceleration without dramatic changes in expansion rate. However, even modest acceleration, sustained over cosmic timescales, produces enormous cumulative effects. The universe 100 billion years from now will be vastly larger, emptier, and colder than today's cosmos. Understanding accelerating expansion reveals that cosmic darkening involves not just the death of light sources, but the fundamental restructuring of spacetime itself. The universe isn't simply running out of fuel, it's actively growing larger and emptier, pulling apart the very foundations of cosmic structure and ensuring that even if new light sources somehow appeared, they would be isolated beyond any possibility of illuminating distant regions of space. This expansion-driven isolation represents a form of cosmic death that's more profound than simple stellar exhaustion. It's the death of cosmic connectivity, cosmic communication, and cosmic coherence, the transformation of a universe filled with interacting structures into a collection of isolated fragments drifting apart in an ocean of ever-expanding emptiness. Chapter 4. Heat Death. Beyond stellar death and cosmic expansion lies an even more fundamental fate that governs the ultimate destiny of the universe: the inexorable march toward maximum entropy, commonly known as heat death. This thermodynamic endpoint represents the final equilibrium state where all useful energy has been dissipated, all temperature differences have been eliminated, and no organized activity can ever occur again. The concept of heat death emerges from the second law of thermodynamics, one of the most fundamental principles in physics. This law states that the entropy of any isolated system tends to increase over time until it reaches maximum possible entropy. Entropy measures the degree of disorder in a system, and the second law essentially says that organized energy spontaneously transforms into disorganized heat, but never the reverse. You can observe this principle in everyday life. Hot coffee cools to room temperature by transferring heat to its surroundings. The organized thermal energy of the hot coffee becomes distributed throughout the environment, increasing overall entropy. Never do you observe room temperature coffee spontaneously heating up by extracting thermal energy from its surroundings, even though this wouldn't violate energy conservation. Applied to the entire universe, the second law of thermodynamics predicts that all organized energy will eventually be converted to heat and uniformly distributed throughout space. Stars burn by converting nuclear fuel into radiant energy, which eventually gets absorbed by matter and re-radiated as lower energy thermal radiation. This process irreversibly increases cosmic entropy while decreasing the universe's capacity for future organized activity. The timescale for universal heat death depends on the specific mechanisms by which entropy increases. Stellar burning represents one major pathway, converting organized nuclear fuel into disorganized radiation. But stars represent only a temporary phase in cosmic evolution. Their lifetimes are finite and their fuel supplies are limited. Once all stars have burned out, the universe will need alternative mechanisms to continue its march toward maximum entropy. After stellar death, the primary entropy-producing processes will involve the gravitational interactions and eventual decay of stellar remnants. White dwarf stars will slowly cool by radiating away their thermal energy, taking roughly 1,015 years to reach the background temperature of space. Neutron stars will follow similar cooling patterns, but over somewhat different timescales, due to their different internal structure and composition. Black holes introduce fascinating complexities to the thermodynamic fate of the universe. According to Stephen Hawking's theoretical calculations, black holes possess temperature and entropy, with smaller black holes being hotter than larger ones. A black hole with the mass of our Sun would have a temperature of roughly 107 Kelvin, far colder than the current cosmic microwave background temperature of 2.7 Kelvin. This means that stellar mass black holes are currently absorbing energy from the cosmic background radiation rather than emitting it. They will continue growing slowly until the universe expands and cools enough that their Hawking temperature exceeds the background temperature. The evaporation process is extraordinarily slow for stellar mass black holes. A black hole with the mass of our Sun would take approximately years to evaporate completely, a timescale so vast that it makes the current age of the universe seem like an instant. Supermassive black holes containing millions or billions of solar masses would take even longer, requiring periods approaching 10,100 years for complete evaporation. During their slow evaporation, black holes will dominate the universe's energy budget and entropy production. They will be the primary source of activity in a cosmos otherwise devoid of energy-generating processes. The universe will transition through what cosmologists call the black hole era, when these slowly evaporating objects provide the only source of new entropy production. The final evaporation of the last black holes will mark a crucial transition point in cosmic evolution. Once all black holes have disappeared, the universe will contain only elementary particles, photons, and perhaps dark matter particles distributed throughout ever-expanding space. These particles will continue to interact occasionally, but the rate of interactions will decrease as cosmic expansion dilutes their density. Even after black hole evaporation, the approach to heat death will continue through increasingly rare and exotic processes. If protons are unstable, as predicted by some theories in particle physics, they will eventually decay into lighter particles and radiation. The predicted proton lifetime is roughly 1,034 years, far longer than the age of the universe, but still finite on cosmic timescales. Proton decay would represent the final dissolution of ordinary matter, converting the atoms that make up planets, stellar remnants, and any surviving complex structures into elementary particles and radiation. This process would eliminate the last vestiges of organization from the cosmic era when stars and galaxies dominated the universe's structure. However, even proton decay doesn't represent the absolute endpoint of thermodynamic evolution. In a universe containing only elementary particles and radiation, quantum fluctuations can still produce occasional interactions and particle creation events. These processes occur at extraordinarily low rates but continue indefinitely, slowly driving the universe toward ever higher entropy states. The quantum vacuum itself possesses energy and can spontaneously create particle pairs through virtual fluctuations. In the far future, when the universe is cold and empty, these quantum processes might become the dominant source of activity. Random quantum fluctuations could occasionally produce more complex structures, though the probability of such events becomes vanishingly small. Some theoretical calculations suggest that given infinite time, quantum fluctuations might eventually produce organized structures purely by chance. Random fluctuations could spontaneously create regions of lower entropy, potentially even forming new planetary systems or biological structures. However, the timescales for such events are unimaginably vast periods that make black hole evaporation seem rapid by comparison. The concept of heat death also depends on the ultimate geometry and fate of space itself. If the universe continues expanding forever, as current observations suggest, then thermal equilibrium will be reached at a temperature approaching absolute zero. All matter and energy will be distributed throughout infinite space, creating a state of maximum entropy at minimum temperature. Alternative cosmic scenarios could produce different thermodynamic endpoints. If cosmic expansion eventually reverses into a big crunch, the universe would heat up rather than cool down, potentially reaching a state of maximum entropy at very high temperature rather than very low temperature. However, current observations of accelerating expansion make this scenario extremely unlikely. The discovery of dark energy complicates thermodynamic predictions about cosmic fate. Dark energy appears to maintain constant density even as space expands, potentially providing an infinite reservoir of energy that could prevent the universe from reaching true thermal equilibrium. However, dark energy density is distributed uniformly throughout space and cannot be concentrated to perform useful work. Some speculative theories propose that dark energy might eventually decay or change its properties, potentially releasing vast amounts of energy that could temporarily reverse cosmic cooling. Such scenarios remain highly speculative and depend on physics beyond our current understanding of dark energy and cosmic evolution. The approach to heat death reveals the temporary nature of all cosmic structure and organization. Stars, galaxies, planets, and life itself represent brief departures from thermal equilibrium, temporary eddies of organization in the universe's inexorable flow toward maximum entropy. The energy gradients that power stellar fusion, biological metabolism, and geological activity will all eventually dissipate into uniform heat. Yet the timescales involved in reaching heat death are so vast that they challenge human comprehension. The universe could sustain complex structure and even life for periods that are millions of billions of times longer than its current age. From a human perspective, the approach to heat death is so slow as to be essentially irrelevant to any conceivable future development. Understanding heat death provides the ultimate context for cosmic evolution and the eventual darkness that awaits the universe. This isn't simply the extinction of light sources, but the fundamental elimination of energy gradients necessary for any organized activity. Heat death represents the final victory of entropy over order, the ultimate equilibrium from which no further change is possible. The thermodynamic fate of the universe reveals that cosmic darkness is more profound than the simple absence of light. It represents the end of cosmic activity itself, a final state where space contains only uniformly distributed matter and energy at thermal equilibrium. In this ultimate darkness, time becomes meaningless because nothing can ever happen to mark its passage. Chapter 5. Vacuum Stability. Beneath the apparent solidity of matter and the vast emptiness of space lies something far more fragile than most people realize. The quantum vacuum itself, which exists in a state so delicately balanced that it could potentially undergo catastrophic transition that would destroy every atom in the universe faster than the speed of light. Understanding vacuum stability reveals one of the most profound and terrifying aspects of cosmic stability: the possibility that the very foundation of reality could spontaneously transform into something completely different, making our current form of existence impossible. The concept of vacuum stability emerges from quantum field theory's description of empty space. In quantum mechanics, what we call empty space or vacuum isn't actually empty at all, but rather represents the lowest possible energy state of quantum fields that permeate all of space and time. These fields constantly fluctuate, even in their ground state, creating virtual particles that briefly appear and disappear according to the uncertainty principle. The vacuum state represents a delicate balance where these fluctuations are minimized but never completely eliminated. But quantum field theory reveals something disturbing about this vacuum state. It might not be the lowest possible energy configuration. If there exists a lower energy state, what physicists call the true vacuum, then our current vacuum could be metastable, meaning it's temporarily stable, but could potentially decay into the true vacuum through quantum tunneling. Such a transition would fundamentally alter the properties of space and time, making our current form of physics impossible and destroying all existing structures in the process. The possibility of vacuum decay was first seriously investigated by Sidney Coleman and Frank DeLucia in 1977. They showed that even if our vacuum is metastable, quantum mechanics allows for the spontaneous formation of bubbles of true vacuum within the false vacuum of our current universe. These bubbles would expand at the speed of light, converting everything they encounter into the new vacuum state. The expansion would be completely undetectable from inside our false vacuum until the bubble wall reached us, at which point physics as we know it would instantly cease to exist. The mathematical description of vacuum decay reveals its connection to the fundamental structure of quantum fields. In quantum field theory, each type of particle corresponds to a quantum field with its own potential energy function. The vacuum state corresponds to the minimum of this potential, but complex fields can have multiple minima: local minima that represent matchable states and a global minimum that represents the true vacuum. Quantum tunneling allows the field to transition from a local minimum to the global minimum, even if there is an energy barrier between them. The standard model of particle physics provides specific predictions about vacuum stability that depend critically on the masses of fundamental particles. The Higgs field, which gives mass to other particles, has a potential that determines whether our vacuum is stable, metastable, or unstable. Precise measurements of the Higgs boson mass, discovered at the Large Hadron Collider in 2012, indicate that the Higgs potential has a structure that makes our vacuum metastable rather than absolutely stable. According to current calculations, the standard model vacuum is stable for energies up to about 1010 GeV, far higher than any energy scales accessible to current experiments. However, at higher energy scales that might have existed in the early universe, the vacuum could become unstable. This creates a potential paradox. If vacuum decay was possible in the early universe, why didn't it occur during the Big Bang when energy densities were enormous? The resolution of this paradox involves the effects of cosmic expansion and temperature on vacuum stability. During cosmic inflation, the rapid expansion of space created conditions where quantum fluctuations were stretched to scales larger than the observable universe. This stretching process could have stabilized the vacuum against decay by preventing the formation of critical bubble nuclei. Additionally, high temperatures in the early universe modify the effective potential of the Higgs field in ways that could enhance stability. Recent calculations by Andre Lind, Renata Kalish, and others have shown that cosmic inflation might not only have preserved vacuum stability, but could have actively selected our current vacuum state from among multiple possibilities. If the universe underwent inflation while exploring different vacuum configurations, only those regions that inflated into stable or long-lived metastable states would produce the large-scale structure we observe today. But vacuum stability involves more than just the Higgs field. The Standard Model contains multiple quantum fields, and their interactions create complex relationships between vacuum stability and fundamental parameters. The masses of quarks, leptons, and gauge bosons all influence the vacuum stability calculations through quantum corrections that modify the effective potential at high energies. Small changes in any of these masses could shift the vacuum from metastable to unstable or vice versa. The discovery of dark energy adds another layer of complexity to vacuum stability. If dark energy represents the energy density of the quantum vacuum, then understanding vacuum stability requires understanding why this energy density has the specific value we observe rather than some other value. The enormous discrepancy between theoretical predictions and observed vacuum energy suggests that our understanding of vacuum physics remains incomplete. Some theoretical approaches to the dark energy problem involve mechanisms that could affect vacuum stability. If dark energy is dynamic rather than constant, it might represent a slowly evolving vacuum state that will eventually decay into a different configuration. Alternatively, if dark energy emerges from extra dimensions or modified gravity, these new physics effects might stabilize or destabilize the vacuum in ways not captured by the Standard Model. The anthropic principle provides one possible explanation for why we observe a stable or long-lived vacuum. In a multiverse, where different regions have different vacuum configurations, only regions with stable vacua could support the long-term existence of stars, planets, and life. Unstable vacua would decay too quickly to allow for the billions of years of stable conditions necessary for biological evolution and the emergence of observers. But anthropic arguments for vacuum stability raise profound questions about the nature of physical law and cosmic evolution. If vacuum stability is maintained by observer selection rather than fundamental physics, it suggests that much of what we observe about the universe might be contingent rather than necessary. The apparent fine-tuning of physical parameters for stability and complexity might reflect our existence as observers in one of the rare regions of the multiverse where such stability is possible. Experimental particle physics provides increasingly precise constraints on vacuum stability through measurements of fundamental particle properties. The Large Hadron Collider and future particle accelerators can measure particle masses and coupling constants with unprecedented precision, allowing for more accurate calculations of vacuum stability. These measurements might reveal whether our vacuum is truly metastable or whether new physics effects stabilize it in ways not captured by current theory. The study of cosmic rays, high-energy particles from space, also provides constraints on vacuum stability. If our vacuum were unstable at currently accessible energies, cosmic ray interactions in the upper atmosphere might occasionally trigger vacuum decay. The fact that we do and observe such events provides evidence that our vacuum is at least stable against perturbations from cosmic ray energies, which extend up to about 1020 electron volts. Vacuum stability also connects to searches for new physics beyond the Standard Model. Many theories that attempt to unify the fundamental forces or explain dark matter and dark energy predict new particles and interactions that could affect vacuum stability. Supersymmetry, extra dimensions, string theory, and the other theoretical frameworks all make specific predictions about vacuum structure that could be tested through particle physics experiments. The implications of vacuum instability for cosmic evolution would be dramatic. If our vacuum is metastable with a finite lifetime, then the universe faces an ultimate deadline beyond which current physics cannot persist. Even if this deadline is far in the future, potentially many times the current age of the universe, it represents a fundamental limit to the long-term evolution of complexity and consciousness. However, vacuum instability would not necessarily mean the end of all possible physics. The true vacuum state would have its own physical laws and could potentially support different forms of structure and organization. But any such structures would be based on completely different physics from what we observe today, making it impossible to predict whether they could support anything analogous to chemistry, biology, or consciousness. Current research on vacuum stability focuses on understanding how quantum corrections, cosmic evolution, and possible new physics affect the long-term fate of the vacuum. Advanced computational techniques allow physicists to calculate vacuum stability with increasing precision, while new theoretical approaches explore how vacuum dynamics might be modified by effects not included in the standard model. The question of vacuum stability thus represents one of the most fundamental aspects of cosmic stability. While dark energy, quantum pressure, and expansion dynamics prevent gravitational collapse and maintain current cosmic structure, vacuum stability determines whether the underlying framework of physics itself can persist indefinitely. Understanding vacuum stability requires integrating quantum field theory, cosmology, and particle physics to determine whether the foundation of reality is truly stable or merely enjoys a temporary reprieve from fundamental transformation. But even if the vacuum proves stable, cosmic stability involves additional mechanisms operating on scales from quantum to cosmic. The next crucial element involves understanding how cosmic inflation not only initiated the expansion that prevents collapse, but also established the initial conditions that determine whether the universe can maintain its current structure indefinitely. Chapter 6. Inflation Mechanics. In the first tiny fraction of a second after the Big Bang, something extraordinary happened that determined whether our universe would be capable of supporting stars, galaxies, and life for billions of years to come. During a period called cosmic inflation, space expanded faster than the speed of light by a factor so enormous that a region smaller than a proton grew to larger than a grapefruit in less than 10 to 32 seconds. This inflationary expansion didn't just create the initial conditions for cosmic structure. It established the fundamental mechanisms that continue to prevent cosmic collapse today. The theory of cosmic inflation was developed in the early 1980s by Alan Guth, Andre Lind, and others to solve several puzzling features of the Big Bang model. The standard Big Bang theory successfully explained the expansion of the universe and the formation of light elements, but it couldn't account for why the universe appears so remarkably uniform on large scales while still containing the small density fluctuations necessary for structure formation. Inflation provided an elegant solution by showing how quantum fluctuations could be stretched to cosmic scales while maintaining overall uniformity. The driving force behind inflation was an inflated field, a hypothetical quantum field with unusual properties that caused it to maintain nearly constant energy density even as space expanded exponentially. Unlike normal matter and radiation, which become diluted as space expands, the inflated field's energy density remained approximately constant during inflation, providing the negative pressure necessary to drive exponential expansion according to Einstein's field equations. This exponential expansion had profound effects on the universe's subsequent evolution. Before inflation, the universe was filled with extreme density fluctuations, curved space-time geometry, and exotic matter from the high-energy physics of the Planck epoch. Inflation stretched space so rapidly that all these irregularities were smoothed away, leaving behind a universe that was extraordinarily flat, uniform, and filled with the gentle density fluctuations that would eventually become galaxies and stars. But inflation did more than just create smooth initial conditions. It established the precise balance between expansion and gravity that continues to prevent cosmic collapse today. The amount of inflation determines the ultimate geometry of space, and observations indicate that our universe underwent exactly the right amount of inflation to produce nearly flat space-time geometry. If inflation had been slightly less, the universe would have positive curvature and would eventually recollapse. If inflation had been slightly more, the universe would have negative curvature and would expand so rapidly that gravity could never assemble matter into structures. The flatness problem reveals one of inflation's most remarkable achievements. The quantum fluctuations that occurred during inflation provide the seeds for all cosmic structure. These fluctuations arose from the uncertainty principle operating on the inflaton field itself. Quantum mechanical variations that normally would remain microscopic were stretched to cosmic scales by inflationary expansion. The statistical properties of these quantum fluctuations determine the distribution of galaxies, the formation of stars, and ultimately the possibility of planetary systems and life. Precise measurements of the cosmic microwave background radiation by satellites like WMAP and Planck have confirmed many detailed predictions of inflationary theory. The temperature fluctuations observed in this ancient light match the statistical properties expected from quantum fluctuations stretched by inflation. These observations provide strong evidence that inflation actually occurred and reveal specific information about the physics operating during this crucial epoch. But inflation's role in preventing cosmic collapse extends beyond establishing initial conditions. The inflationary epoch demonstrates that the universe has access to forms of matter and energy that can drive accelerating expansion even in the presence of strong gravitational fields. This provides a proof of concept that accelerating expansion can overcome gravity under extreme conditions, validating the mechanisms that prevent collapse in the current universe through dark energy. The connection between inflation and dark energy might be more than just conceptual similarity. Some theoretical models propose that dark energy represents a continuation or echo of the inflationary process. If the inflaton field never completely decayed after inflation ended, its residual energy density could contribute to or even constitute dark energy. This would mean that the same physics responsible for preventing early collapse continues to prevent late-time collapse. Recent theoretical work has explored the possibility that inflation might be an ongoing process in the universe at large. In eternal inflation models, developed by Andrea Lind and others, inflation continues forever in most regions of space, while occasionally ending in finite regions that become observable universes like ours. This eternal inflation would create a multiverse containing infinite numbers of universes with different properties, most of which would not support structure formation or consciousness. The multiverse implications of eternal inflation provide another perspective on cosmic stability. If inflation produces countless universes with different properties, then the remarkable stability and fine-tuning we observe might not require special physics, but simply reflect observer selection. We exist in one of the rare universes where conditions allow for long-term structure and complexity. Most universes in the eternal inflation multiverse would either collapse immediately or expand too rapidly for structure formation. But eternal inflation raises profound questions about the nature of cosmic stability and the uniqueness of our cosmic environment. If our universe is just one of infinitely many produced by eternal inflation, then the mechanisms preventing collapse might be much more fragile and contingent than they appear. Small changes in fundamental physics or initial conditions might lead to universes where these mechanisms fail catastrophically. The physics of inflation also reveals connections between cosmic stability and high-energy particle physics. The inflaton field likely had energies comparable to those required for grand unification of the fundamental forces, around 1016 GeV. Understanding inflation therefore requires understanding physics at energy scales far beyond current experimental reach, connecting cosmic stability to the deepest levels of fundamental physics. Some inflationary models predict that inflation was preceded by even more exotic phases of cosmic evolution involving string theory, extra dimensions, or quantum gravity effects. These pre-inflationary epochs might have established the initial conditions for inflation itself, creating a hierarchy of mechanisms that ensure cosmic stability across multiple levels of physical description. The study of inflation has also revealed potential instabilities that could threaten cosmic evolution. If the inflaton field is not completely stable in its post-inflationary state, it might undergo phase transitions that could restart inflation in localized regions. Such bubble nucleation events would create expanding regions where space-time geometry and physical constants differ from our current environment, potentially destroying existing structure. Current observational cosmology aims to detect direct evidence of inflation through measurements of primordial gravitational waves, ripples in space-time itself that were generated by quantum fluctuations during inflation and stretched to observable scales. These gravitational waves would provide a direct probe of the physics operating during inflation and could reveal information about the energy scale and dynamics of the inflationary process. The detection of primordial gravitational waves would confirm that inflation involved enormous energies comparable to those required for quantum gravity effects. This would connect cosmic stability directly to the most fundamental aspects of physics, showing that the mechanisms preventing collapse operate at the deepest level of physical law rather than being accidents of cosmic evolution. But inflation mechanics also demonstrate the incredible efficiency with which cosmic processes can establish stability. In less than 10 to 32 seconds, inflation solved multiple fine-tuning problems, established the initial conditions for 13.8 billion years of cosmic evolution, and created the quantum fluctuations that would eventually become every star and galaxy in the observable universe. This efficiency suggests that cosmic stability might not require ongoing fine-tuning, but could be established through robust physical processes that naturally produce stable, long-lived cosmic environments. The inflationary solution to cosmic stability problems provides a template for understanding how fundamental physics can create self-organizing, self-stabilizing systems. The same principles that allowed inflation to solve the horizon flatness and monopole problems might operate throughout cosmic evolution to maintain stability against various forms of collapse and instability. Modern research in inflationary cosmology focuses on understanding the detailed physics of the inflationary transition and its connections to particle physics and quantum gravity. Advanced theoretical frameworks like string theory and loop quantum gravity make specific predictions about inflationary dynamics that could be tested through precision cosmological observations. The mechanics of inflation therefore represent a crucial component of cosmic stability, not just through establishing appropriate initial conditions, but through demonstrating that accelerating expansion can overcome gravitational collapse even under extreme conditions. But inflation operates in the context of a larger framework of cosmic evolution that includes the formation and evolution of bound structures that must maintain their integrity against various disruptive forces. Understanding how these bound structures maintain their stability requires examining the delicate balance of forces operating within galaxies, star systems, and other cosmic structures that manage to persist as coherent entities, even while embedded in an expanding, evolving cosmic environment. This structural stability represents another layer in the universe's defense against gravitational and other forms of collapse. Chapter 7. Structural balance within every galaxy, around every star, and throughout every planetary system. A delicate choreography of forces maintains structural integrity against the constant threat of gravitational collapse. This structural balance operates through a complex interplay of rotation, thermal pressure, nuclear processes, and electromagnetic forces that work together to create stable configurations of matter that can persist for billions of years. Understanding this balance reveals how the universe creates a lasting structure at every scale while avoiding both collapse and dispersal. The most dramatic example of structural balance occurs in stars themselves, where nuclear fusion in stellar cores generates outward pressure that exactly balances the inward pull of gravity for billions of years. This hydrostatic equilibrium represents one of nature's most precise balancing acts. If nuclear reactions were slightly stronger, stars would explode. If they were slightly weaker, stars would collapse. The fact that stars can maintain this balance for timescales much longer than human civilization demonstrates the robustness of the physical processes involved. The nuclear processes that power stars depend on quantum mechanics in subtle ways that contribute to structural stability. Nuclear fusion requires extremely high temperatures and pressures to overcome the electrical repulsion between atomic nuclei. But once fusion begins, it's naturally self-regulating. If the stellar core becomes hotter and denser, fusion rates increase, generating more energy and pressure that pushes the core back toward equilibrium. This negative feedback mechanism provides automatic stability against runaway fusion or collapse. But stellar stability involves more than just nuclear physics. The transport of energy from stellar cores to their surfaces occurs through radiation and convection processes that create additional stabilizing mechanisms. Energy transport through radiation is naturally stable. If energy production increases in the core, the increased radiation pressure helps restore equilibrium. Convective energy transport, while more complex, also contributes to stability by efficiently redistributing energy and maintaining appropriate temperature gradients. The evolution of stars over cosmic time reveals how structural balance adapts to changing conditions. As stars consume hydrogen in their cores, the nuclear fuel becomes depleted and core temperatures rise in response to gravitational compression. This heating ignites new fusion reactions involving heavier elements, allowing stars to maintain energy production and structural stability even as their composition changes. The progression from hydrogen burning to helium burning to carbon burning demonstrates the universe's capacity to create new forms of structural balance as physical conditions evolve. Galaxy structure provides another example of how rotation and gravity combine to create stable configurations. Spiral galaxies, like the Milky Way, maintain their structure through a balance between gravitational attraction that tries to pull matter toward the galactic center and centrifugal force from rotation that opposes this contraction. This balance allows galaxies to maintain coherent disk structures for billions of years while continuing to form new stars and evolve chemically. But galactic structural balance involves complications that weren't fully understood until the discovery of dark matter. Observations of galaxy rotation curves, how orbital velocity varies with distance from the galactic center, revealed that galaxies contain far more mass than can be accounted for by visible stars and gas. This dark matter provides additional gravitational binding that stabilizes galactic structure against disruption from internal motions and external influences. The dark matter component of galaxies demonstrates how structural balance depends on components that aren't directly observable but are essential for stability. Dark matter halos provide the gravitational scaffolding that allows ordinary matter to assemble into galaxies while maintaining stability against tidal forces from neighboring galaxies and the general expansion of the universe. Without dark matter, galaxies would likely be much smaller, more fragile, and shorter-lived than what we observe. Planetary system formation illustrates how structural balance emerges from initially chaotic conditions through processes that naturally lead to stable configurations. When stars form from collapsing gas clouds, they're surrounded by rotating disks of material that gradually condense into planets through gravitational assembly. The final planetary systems that emerge represent solutions to the complex gravitational dynamics of multiple interacting bodies orbiting a central star. The stability of planetary orbits depends on precise relationships between orbital periods, eccentricities, and mutual gravitational perturbations. Most planetary systems settle into configurations where orbital periods have simple mathematical relationships that minimize long-term instabilities. These resonant configurations demonstrate how gravitational dynamics naturally evolve towards stable states that can persist for the age of the solar system. But planetary system stability also requires protection against external disruptions. The outer planets in our solar system, particularly Jupiter, act as gravitational shields that deflect comets and asteroids away from the inner planets where Earth resides. This protection is essential for maintaining the stable conditions necessary for long-term biological evolution. Systems without such protection would experience frequent bombardments that would disrupt the development of complex life. The structural balance of complex systems like galaxies and planetary systems emerges from what physicists call hierarchical stability. Smaller subsystems maintain their integrity while embedded within larger systems that also maintain their integrity. Stars maintain internal balance while orbiting stably within galaxies that maintain their overall structure while embedded in the expanding cosmic web. This hierarchical organization allows for stability across a vast range of scales simultaneously. Thermal equilibrium provides another crucial aspect of structural balance that operates across multiple scales. Stars, planets, and even galaxies maintain approximately constant temperatures over long periods through balance between energy input and energy output. This thermal stability is essential for maintaining chemical and nuclear processes that support complex structure. Without thermal balance, systems would either heat up until they dispersed or cool down until all activity ceased. The study of structural balance has revealed deep connections between stability and information processing. Complex systems that maintain structural integrity over long periods necessarily develop mechanisms for storing and processing information about their environment and history. Galaxies, remember, their formation history through their chemical composition and stellar populations. Planets maintain information about their thermal and chemical evolution in their geological structure. Living systems represent the most sophisticated examples of structural balance, maintaining complex organization through metabolism that extracts energy from their environment and uses it to create and maintain structural complexity. Biological organisms demonstrate how structural balance can support not just persistence, but active growth, reproduction, and evolution toward greater complexity. The emergence of biological structural balance from non-living chemical systems illustrates how the universe's capacity for stability extends beyond simple gravitational and nuclear processes to include self-organizing systems that create their own stability mechanisms. Life represents a new form of structural balance that actively maintains itself through interaction with its environment rather than simply persisting through passive equilibrium. But all forms of structural balance ultimately depend on the universe maintaining conditions that allow for the phi persistence of complex structures over cosmological timescales. This requires not just local stability, but cosmic stability. The expansion rate, dark energy density, and fundamental constants must remain within ranges that permit lasting structure formation and evolution. Recent observations of cosmic evolution reveal that structural balance has been maintained throughout most of cosmic history, but faces challenges in the far future. As dark energy becomes increasingly dominant, it will eventually overcome the gravitational binding of galaxy clusters and ultimately even individual galaxies. This represents a fundamental limit to how long current forms of structural balance can persist in an accelerating universe. The study of structural balance also reveals potential solutions to long-term cosmic challenges. Advanced civilizations might develop technologies that can maintain structural integrity even as cosmic conditions change. Artificial structures powered by controlled nuclear fusion or other advanced energy sources might persist even after natural stars cease to form and existing stars burn out. Understanding structural balance, therefore, provides insights into both current cosmic stability and future possibilities for maintaining complexity in an evolving universe. The mechanisms that currently maintain structural integrity across cosmic scales demonstrate the universe as remarkable capacity for self-organization and stability, while also revealing the boundaries and limitations that constrain how long such stability can persist. The hierarchical nature of structural balance, from stellar cores to galactic disks to planetary systems, shows how stability at one level supports stability at other levels, creating a network of mutual support that enhances overall cosmic stability. But this network also creates dependencies where instability at one level can cascade to affect stability at other levels. Modern astrophysics focuses on understanding these interconnections and identifying potential failure modes where structural balance might break down catastrophically. Computer simulations of galactic evolution, stellar dynamics, and planetary system formation provide detailed models of how structural balance operates and evolves over cosmic time. The future evolution of structural balance will likely involve new forms of organization and stability that don't exist in the current universe. As cosmic conditions change, and potentially as intelligence spreads throughout the cosmos, new mechanisms for maintaining complex structure might emerge that extend the universe's capacity for stability far beyond what natural processes alone can achieve. But structural balance represents only one layer in the universe's multi-level defense against collapse and dissolution. Understanding cosmic stability requires examining how all these mechanisms, from quantum pressure to cosmic expansion to structural balance, work together to create a universe capable of supporting lasting complexity and consciousness. Chapter 8. Force equilibrium at every scale of cosmic structure. From the quantum realm to galactic superclusters, the universe maintains its stability through an extraordinary orchestration of forces that counterbalance each other with mathematical precision. This force equilibrium doesn't happen by accident. It emerges from fundamental symmetries and conservation laws that operate throughout the cosmos, creating a self-regulating system where any disturbance automatically generates restoring forces that prevent catastrophic collapse or dissolution. The foundation of force equilibrium lies in the four fundamental interactions that govern all physical processes: gravity, electromagnetism, and the strong and weak nuclear forces. Each of these forces operates according to different principles, affects different types of matter, and dominates at different scales. But together, they create a complex web of interactions that maintains cosmic stability across an enormous range of conditions and environments. Gravity, while the weakest fundamental force, dominates on the largest scales due to its universal attraction and unlimited range. Every piece of matter in the universe attracts every other piece according to Newton's inverse square law, creating gravitational fields that extend across cosmic distances. This universal attraction would normally lead to catastrophic collapse, but it is balanced by the expansion of space itself and the repulsive effects of dark energy that prevent runaway gravitational compression. The electromagnetic force provides crucial balance at intermediate scales through both attractive and repulsive interactions. Unlike gravity, which only attracts, electromagnetic forces can repel as well as attract, creating complex equilibria that support atomic structure, molecular chemistry, and the large-scale properties of matter. The electromagnetic repulsion between electrons prevents atoms from collapsing under gravitational or nuclear attraction, while electromagnetic attraction between opposite charges holds atoms and molecules together. Within atomic nuclei, the strong nuclear force creates another layer of force equilibrium that prevents both nuclear collapse and nuclear explosion. The strong force attracts protons and neutrons together with enormous strength over very short ranges. Overcoming the electromagnetic repulsion between positively charged protons that would otherwise tear nuclei apart. This nuclear binding provides the foundation for stable matter and the nuclear reactions that power stars. The weak nuclear force, while not directly involved in structural stability, plays a crucial role in regulating nuclear processes that could otherwise lead to runaway reactions. Beta decay processes mediated by the weak force allow unstable nuclei to reach more stable configurations, preventing the accumulation of highly unstable matter that could undergo explosive decay. This regulation helps maintain the nuclear stability necessary for long-lived stars and planets. But force equilibrium involves more than just the fundamental interactions. It also depends on emergent forces that arise from the collective behavior of many particles. Thermal pressure from random molecular motion provides crucial support against gravitational compression in stars and planets. This thermal pressure naturally adjusts to changing conditions. If gravitational compression increases temperature, thermal pressure increases proportionally, automatically providing enhanced resistance to further compression. Quantum mechanical effects create additional forces that contribute to cosmic stability. Degeneracy pressure from the Pauli exclusion principle prevents electrons from occupying the same quantum states, creating outward pressure that supports white dwarf stars against gravitational collapse. Similar quantum pressure from neutrons supports neutron stars, while quantum chromodynamic effects involving quarks and gluons might provide pressure in even more extreme environments. The balance of forces within stars demonstrates how multiple equilibria can operate simultaneously to maintain stability. Hydrostatic equilibrium balances gravitational compression against thermal and radiation pressure. Nuclear equilibrium balances the production of energy through fusion against the transport of energy to the stellar surface. Thermal equilibrium balances energy generation in the stellar core against energy radiation from the stellar surface. These multiple equilibria interact in complex ways that enhance overall stability. If nuclear energy production increases, thermal pressure increases, causing stellar expansion that reduces core density and temperature, automatically reducing nuclear reaction rates back toward equilibrium. This negative feedback mechanism ensures that stars remain stable against perturbations that would otherwise cause runaway fusion or collapse. Galactic force equilibrium involves additional complications due to rotation and the presence of dark matter. The centrifugal force from galactic rotation balances gravitational attraction to maintain stable disk structures, while pressure from stellar motions provides support against compression in galactic bulges and halos. Dark matter contributes additional gravitational binding that helps maintain galactic integrity against tidal forces and internal disturbances. The cosmic web of galaxy filaments and voids represents force equilibrium on the largest observable scales. Gravitational attraction along filaments is balanced by expansion in the transverse directions, creating elongated structures that can persist for billions of years. The voids between filaments represent regions where expansion dominates over gravitational attraction, creating large-scale structure that's neither completely uniform nor completely collapsed. But force equilibrium is not static. It evolves over cosmic time as the relative importance of different forces changes. In the early universe, radiation pressure dominated over gravitational attraction, preventing structure formation until the universe cooled sufficiently for matter to become gravitationally dominant. The transition from radiation domination to matter domination represents a fundamental shift in force equilibrium that enabled the formation of stars and galaxies. The more recent transition to dark energy domination represents another fundamental shift in cosmic force equilibrium. As dark energy becomes increasingly important relative to matter and radiation, it will eventually overcome gravitational attraction, even within currently bound systems like galaxy clusters. This represents a future transition where force equilibrium shifts toward expansion and dispersion rather than gravitational binding. The study of force equilibrium has revealed deep connections between cosmic stability and fundamental symmetries in physics. Conservation laws for energy, momentum, and angular momentum emerge from symmetries in the laws of physics, and these conservation laws constrain how forces can interact to maintain equilibrium. The remarkable stability of cosmic force balance might reflect these fundamental symmetries rather than requiring fine-tuning of force strengths. Gauge symmetries in particle physics determine the relative strengths of electromagnetic and nuclear forces through the structure of quantum field theory. If these symmetries are exact and fundamental, then the force ratios we observe might be inevitable consequences of the mathematical structure of reality, rather than contingent facts that could have been different. Recent developments in string theory and other approaches to quantum gravity suggest that the apparent fine-tuning of force strengths might emerge from deeper principles involving extra dimensions, supersymmetry, or other exotic physics. These theoretical frameworks predict specific relationships between force strengths that could explain why the universe achieves such precise force equilibrium. But force equilibrium also reveals potential instabilities that could disrupt cosmic stability. If fundamental constants slowly evolve over cosmic time, force equilibria that are stable today might become unstable in the future. Observations of distant quasars and other cosmic sources provide constraints on how much fundamental constants can change, but they cannot completely rule out slow evolution that could affect long-term stability. Phase transitions in quantum fields could also disrupt force equilibria by changing the effective strengths of fundamental interactions. If the universe undergoes vacuum decay or other phase transitions, the resulting changes in force relationships could destabilize existing structures and prevent the formation of new complexity. The anthropic principle provides one perspective on force equilibrium by suggesting that we observe precisely balanced forces because imbalanced forces would not support the existence of observers. In a multiverse with different force ratios in different regions, only regions with appropriate balance could produce stars, planets, chemistry, and life. The remarkable force equilibrium we observe might reflect observer selection rather than fundamental physics. But regardless of whether force equilibrium reflects fundamental principles or anthropic selection, it provides a crucial component of cosmic stability that operates across all scales and throughout cosmic history. The mathematical precision with which different forces balance each other demonstrates the universe's capacity for self-regulation and self-organization. Understanding force equilibrium also provides insights into how cosmic stability might be maintained or enhanced through technological intervention. Advanced civilizations might develop methods for manipulating fundamental forces to maintain equilibrium even as cosmic conditions change. Such interventions could potentially extend the universe's capacity for supporting complex structures and processes. The network of force equilibria that maintains cosmic stability represents one of the most remarkable features of our universe. A vast interconnected system where forces automatically adjust to maintain stability across dozens of orders of magnitude in scale and energy. This system demonstrates that cosmic stability isn't fragile or accidental, but emerges robustly from the fundamental structure of physical law. But force equilibrium operates within the context of cosmic evolution and the ongoing expansion that carries the universe toward its ultimate fate. Understanding how these equilibria will evolve as the universe continues to expand and cool requires examining the deep thermodynamic principles that govern cosmic evolution and determine whether current stability mechanisms can persist indefinitely or will eventually be overcome by inexorable physical processes.